When dealing with a 2000 amp switchgear panel, conductor sizing is a crucial aspect that demands careful consideration. The initial observation that 350 kc mil conductors may not be adequate for a 2000 amp service is valid and warrants a detailed explanation. The National Electrical Code, or NEC, serves as the primary standard for electrical installations, and it provides guidelines for determining the appropriate conductor size based on ampacity. Ampacity refers to the current carrying capacity of a conductor, which is the maximum amount of current, measured in amps, a conductor can handle continuously without exceeding its temperature rating. According to the NEC, the ampacity of a 350 kc mil copper conductor installed in a raceway is typically around 400 amps. This value, however, is subject to adjustment based on several factors. Firstly, the number of conductors in the raceway significantly impacts ampacity. When multiple current-carrying conductors are bundled together in a single raceway, the heat generated by each conductor increases the overall temperature within the raceway. This elevated temperature reduces the ability of each conductor to dissipate heat effectively, leading to a decrease in their ampacity. The NEC provides specific rating factors in Table 310.15 A3 to account for this effect. For instance, if there are more than 3 current-carrying conductors in a raceway, the ampacity of each conductor must be reduced by a certain percentage depending on the total number of conductors. Secondly, the type of raceway also plays a role in determining conductor ampacity. Different types of raceways, such as rigid metal conduit, electrical metallic tubing, or flexible metal conduit, have varying thermal properties. Some raceways are more effective at dissipating heat than others, which can affect the conductor's ampacity. For example, a rigid metal conduit (RMC) typically provides better heat dissipation compared to a flexible metal conduit (FMC). Thirdly, NEC requirements mandate that the ampacity of the conductors must be equal to or greater than the maximum load current they are intended to carry. In the case of a 2000 amp switchgear panel, the conductors supplying the panel must have a combined ampacity of at least 2000 amps. Given that each 350 kc mil conductor has an ampacity of approximately 400 amps, 4 sets of these conductors would provide a total ampacity of 1600 amps, which falls short of the required 2000 amps. Therefore, based on these considerations, it is likely that the proposed conductor size is insufficient for the 2000 amp switchgear panel. To ensure a safe and reliable electrical installation, it is advisable to upgrade to a larger conductor size. Options such as 500 kc mil or 600 kc mil conductors may be more appropriate, as they offer higher ampacity ratings. However, the final conductor size selection should be based on a comprehensive analysis that takes into account all relevant factors, including the number of conductors in each raceway, the type of raceway, the ambient temperature, and any applicable rating factors. It's also crucial to consider voltage drop. Over long distances, the voltage at the load end of the conductor can be significantly lower than the source voltage due to the conductor's resistance. This voltage drop can negatively impact the performance of equipment connected to the switchgear panel. The NEC recommends limiting voltage drop to a maximum of 3% for branch circuits and 5% for feeders. To mitigate voltage drop, larger conductor sizes may be necessary, even if the ampacity of the smaller conductors is adequate for the load current. In addition to conductor size, the type of insulation used in the conductors also affects their ampacity. Conductors with higher temperature ratings, such as those with THHN or XHHW insulation, can operate at higher temperatures and thus have higher ampacity ratings compared to conductors with low temperature ratings. When selecting conductors, it is important to choose those with an appropriate insulation type for the application and the ambient temperature conditions. The length of the conduit run should be considered, as longer runs can increase voltage drop and may require larger conductors to compensate. Bends and elbows in the conduit can also affect ampacity by increasing the resistance of the conductor and making it more difficult to pull the conductors through the conduit. To minimize these effects, it is recommended to use as few bends as possible and to use proper pulling techniques. Furthermore, the terminations of the conductors at both the switchgear panel and the source equipment must be properly installed and torqued to ensure a secure and reliable connection. Loose or improperly torqued connections can cause overheating and lead to equipment failure or even fire. Therefore, it is essential to follow the manufacturer's instructions and use calibrated torque wrenches when making these connections. Grounding is another critical aspect of electrical installations that must be carefully considered. The grounding system provides a path for fault current to flow back to the source, which helps to protect equipment and personnel from electrical shock. The size of the grounding conductor must be adequate to handle the maximum fault current that could occur in the system. The NEC provides guidelines for determining the appropriate size of the grounding conductor based on the size of the service entrance conductors. Surge protection is also an important consideration for switchgear panels, especially in areas that are prone to lightning strikes or other electrical disturbances. Surge protective devices, or SPDs, can help to protect sensitive electronic equipment from damage caused by voltage surges. SPD should be installed at the switchgear panel and at other critical locations throughout the electrical system. Finally, it is essential to consult with a qualified electrician or electrical engineer to ensure that the electrical installation meets all applicable codes and standards and is safe and reliable. These professionals have the knowledge and experience to properly design and install electrical systems that meet the specific needs of the application. When dealing with high amperage equipment like a 2000 amp switchgear panel, it is crucial to prioritize safety and adhere to all applicable codes and standards. Improperly sized conductors or inadequate grounding can have serious consequences, including equipment failure, electrical shock, and fire. Therefore, it is always best to err on the side of caution and seek expert advice when designing and installing electrical systems. In summary, when evaluating the adequacy of 350 kc mil conductors for a 2000 amp switchgear panel, the following factors should be taken into account. Firstly, the ampacity of the conductors must be equal to or greater than the maximum load current. Secondly, the number of conductors in the raceway, the type of raceway, and the ambient temperature can all affect conductor ampacity. Thirdly, voltage drop, conductor insulation type, conduit length, and the number of bends in the conduit should also be considered. Fourthly, proper termination and grounding techniques are essential for a safe and reliable electrical installation. Fifthly, surge protection may be necessary to protect sensitive equipment from voltage surges. And sixthly, it is always best to consult with a qualified electrician or electrical engineer to ensure that the electrical installation meets all applicable codes and standards. By carefully considering these factors, it is possible to ensure that the electrical system is safe, reliable, and meets the specific needs of the application. Remember that the NEC is updated regularly, so it is important to stay current with the latest requirements. Additionally, local codes and regulations may have specific requirements that must be followed. When in doubt, it is always best to seek expert advice from a qualified electrician or electrical engineer. They can help to ensure that the electrical installation is safe, reliable, and meets all applicable codes and standards. The NEC provides tables for ampacity ratings of conductors, typically found in Article 310. These tables list the allowable ampacities for various conductor sizes and insulation types, based on factors such as the ambient temperature and the number of conductors in a raceway or cable. It is crucial to consult these tables and apply any necessary directing factors to determine the appropriate conductor size for a given application. For example, NEC Table 310.15 B16 provides ampacity ratings for conductors rated 0 through 2000 volts based on an ambient temperature of 30 degrees Celsius or 86 degrees Fahrenheit. If the ambient temperature is higher than 30 degrees Celsius, a temperature correction factor must be applied to reduce the allowable ampacity. Similarly, if there are more than 3 current-carrying conductors in a raceway or cable, a directing factor must be applied to account for the increased heat generated by the conductors. The NEC also provides guidelines for calculating voltage drop in conductors. Voltage drop occurs when the voltage at the load end of the conductor is lower than the source voltage due to the conductor's resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to a maximum of 3% for branch circuits and 5% for feeders. To calculate voltage drop, the following formula can be used. Voltage drop equals 2xk/xi/cm, where voltage drop is the voltage drop in volts, K is the direct current resistance factor for the conductor material, L is the length of the conductor in feet, I is the current in amps, and cm is the circular mils of the conductor. The value of K varies depending on the conductor material. For copper, K is typically around 12.9 ohms circular mils per foot. For aluminum, K is typically around 21.2 ohms circular mils per foot. The circular mils cm of a conductor can be found in NEC Chapter 9, Table 8. By using this formula, it is possible to calculate the voltage drop for a given conductor size and load current. If the calculated voltage drop exceeds the recommended limits, a larger conductor size may be necessary to reduce the voltage drop. In addition to conductor size, the type of overcurrent protection used in the electrical system is also important. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect conductors and equipment from damage caused by excessive current flow. The overcurrent protection device must be sized appropriately to protect the conductors from overload and short-circuit conditions. The NEC provides guidelines for selecting the appropriate overcurrent protection device based on the ampacity of the conductors and the type of equipment being protected. It is important to note that the overcurrent protection device should never be sized larger than the ampacity of the conductors it is protecting. Doing so can create a fire hazard and void the equipment warranty. In addition to the NEC, other codes and standards may also apply to electrical installations. These may include local building codes, fire codes, and safety standards. It is important to be familiar with all applicable codes and standards and to ensure that the electrical installation meets all requirements.